So in this video, we're going to look at the extreme value theorem applied in a case where we have trigonometric functions. And this will be the most complicated of the examples that we've looked at. So again, when we're looking for extrema, the largest and smallest outputs of a function using the extreme value theorem, we're working over a closed interval. We have to define a closed interval over which we're interested in finding the extrema. And then step one, as it has been in the previous videos, is to find the critical numbers. So we know that the extreme values are either going to occur on the endpoints of the interval. So here I'm working on the interval from 0 to 2 pi. There are the endpoints. So the endpoints are candidates for being the max or min values on the closed interval. And we need to look at places where the derivative is equal to 0. We're looking for those relative minima or maxima. So just glancing through this picture, there's no cusp, but I do have 4 places where the tangent lines have slopes of 0. So those, I'm expecting, when I take the derivative and set it equal to 0, I'm expecting to get 4 different critical numbers coming out of that process. So step one is find the critical numbers of the function, because the high and low outputs on the closed interval may occur at those critical numbers. So in this case, we have the trigonometric function f of theta equals 2 times sine theta minus the cosine of twice theta. And then we're going to need to take the derivative so we can set it equal to 0 and find the critical numbers, the values for theta at which the relative max and min are occurring. So the derivative of 2 sine theta will be 2 times the cosine of theta, minus the derivative of the cosine is minus the sine, and it's going to be minus the sine of 2 theta. And then we have a chain rule situation because we have the function twice theta inside of the cosine function. So now I need to multiply by 2 the derivative of twice theta. So this gives me 2 cosine theta. A double negation is a plus, and I have 2 times the sine of 2 theta. And then what I want to remember from trigonometry, right now the periods aren't matching, so this will be a little difficult to solve this trigonometric function. So a technique from trigonometry is to use trig identities to get the periods to match. And I want to remember that the sine of 2 theta is the same as 2 sine theta cosine theta. So I'm going to make that substitution. So we get 2 cosine theta plus 2 times, and the sine of 2 theta can be replaced with 2 sine theta cosine theta. Once I get the periods to match, excuse me, I want to see if I can do any factoring, because I'd like to use the zero product property to find the zeros of the derivative. And actually I took the derivative, so this should say f prime right here. And so what I want to notice is that 2 times the cosine shows up in both terms. So I can factor 2 times the cosine of theta off, which will leave me 1 plus 2 times the sine function left behind. So this is my f prime of theta. So if I want to know when the derivative is equal to 0, I can use the zero product property to say either the cosine of theta needs to be equal to 0, or 1 plus 2 times the sine of theta needs to be equal to 0. So to find those critical numbers, I'm going to set my derivative equal to 0. And setting my derivative equal to 0 means that either the cosine needs to equal 0, or by the zero product property, 1 plus 2 times the sine of theta needs to equal 0. I need to solve these equations over the interval, closed interval from 0 to 2 pi. So I only want solutions on these intervals. So remember, when we solve trigonometric functions, we get infinitely many solutions. But because we're working on the closed interval from 0 to 2 pi, we only want critical numbers in that interval. So in the interval from 0 to 2 pi, theta, cosine of theta will equal 0 when theta is equal to pi over 2, when we're on that quadrantal angle. So remember, on the unit circle, the x-coordinate will be 0 here. We get 0, 1, and right here we have 0, negative 1, and this angle is pi over 2, and this angle is 3 pi over 2. So 3 pi over 2 is a solution for cosine theta equals 0 on the interval from 0 to 2 pi. And now I need to solve this one as well. So I would subtract 1 from both sides and then divide by 2. So we see that the sine of theta needs to equal -1 from subtracting the 1 from both sides and then dividing by 2 to isolate the sine function. So we are asking the question, when is the sine of theta equal to -1/2 on the interval from 0 to 2 pi? So again, that's a unit circle question. And so what we need to remember from trigonometry is that at pi over 6, we have the ordered pair square root of 3 over 2 comma 1/2 on the unit circle. But we need -1/2, so reflecting this point down into quadrant 4, we would have square root of 3 over 2 comma -1/2. And then reflecting through the origin, we would get negative square root of 3 over 2 comma -1/2. So the y-coordinate on the unit circle will be -1/2 in those two locations. And this location here is going to be, it's 6 pi over 6 to here, so 7 pi over 6. So theta equals 7 pi over 6, or rotating theta all the way through to here, that angle is going to be 11 pi over 6. So 11 pi over 6. So we get 4 critical numbers, which matches what the picture is leading us to expect. So again, graphing your function over the closed interval you're interested in is important because it shows you how many solutions that you expect to get, which then if you don't get both solutions for theta, you know that you've made a mistake and you have to rethink what you've done. So there I've established my 4 critical numbers. So remember, step 2 in the process is to evaluate my function at the critical number. So I'm going to slip through to the next slide where I've written down the critical numbers, and this is just giving me some more white space to work with so I have room to do the calculations. So step 2 is to plug in each of the critical numbers into the function and find the function outputs that go with those critical numbers. Again, the graph is useful because it's showing me kind of what I'm expecting. This is about -3/2 here and here, and this is right at about an output of -1. So I have the picture up so I know what I'm expecting. That way if I make a mistake, I can catch my arithmetic errors. So plugging in the first critical number, we do f of pi over 2 is equal to 2 times the sine of pi over 2 minus cosine of 2 times pi over 2 equals, so the sine of pi over 2 is going to equal 1, right? Because on the unit circle at pi over 2, we have the ordered pair 0, 1, and the y-coordinate is the sine. So we get 2 times 1 is 2, minus, those 2's will give us a 1, so it's really going to be 1 times pi, or the cosine of pi. And the cosine of pi, we're looking at this point over here, where we have a -1 and 0, so the x-coordinate's -1. I don't know why I got tongue-tied on that. So we get a double negation is 2 plus 1 is 3. So here is the angle pi over 2, and it is corresponding to that output of 3. So you now catalog, as you calculate those values, you want to catalog them because step 4 is to compare all of the outputs we get. So f of pi over 2 is 3. Now we need to calculate f of 3 pi over 2, which is going to equal 2 times the sine of 3 pi over 2 minus the cosine of 2 times 3 pi over 2. So the sine of 3 pi over 2, that's going to have us down in this position. So it's 3 pi over 2 sitting here. And this is, x is 0, y is -1. So we're going to get 2 times -1 is -2. And then here, this is going to cancel again. So I'm going to get my minus from here. And 3 pi, what we want to recognize is 3 pi is the same as 2 pi plus pi. So every 2 pi radians, you get an angle that's coterminal with an angle on the interval from 0 to 2 pi. So 3 pi is coterminal with pi. So this is the same as the cosine of pi. And the cosine of pi is just -1, so we get -2 minus -1 is, there's a double negation, we get -2 plus 1 is just -1. Here's my 3 pi over 2 corresponding to that output of -1. So f of 3 pi over 2 is -1. And then we just keep grinding through. Now we need to do 7 pi over 6. So we're doing f of 7 pi over 6 equals 2 times the sine of 7 pi over 6. That's a horrible 7. And then it's minus the cosine of 2 times 7 pi over 6. And we know that sine of 7 pi over 6 is -1/2. So we're getting a -1 out of this. Minus, now we need to figure out what to do with this. I want to recognize that 2 will go into 6 3 times. So I really have a 7 pi over 6, or sorry, 3 sitting there. And notice that 3 goes into 7 twice with one little guy left over. So we get 2 plus 7/3 is the same as 2 plus 1/3, right? 3 goes into 7 twice with a remainder of 1, and this is times pi. So we get 2 pi plus pi times 1/3 is pi over 3. So the angle 7 pi over 3 is coterminal with the angle pi over 3. If you rotate 2 pi radians, which is one full circle around the unit circle, we get from pi over 3 right back to itself at 7 pi over 3. So this is really the same as cosine of pi over 3 using the idea of coterminal angles from trigonometry. And the cosine of pi over 3, so on the unit circle, we just want to recognize that pi over 3, if we're sitting on the unit circle, is that 60-degree angle sitting up here. That's pi over 3, where the x-coordinate's 1/2 and the y-coordinate is √3 over 2. So we're going to get -1 minus 1/2 is -3/2. So f of 7 pi over 6 is -3/2. And now I need to do another calculation, so I'm going to erase this stuff here I've already done to give myself some space to work with. Which it's okay to erase because you can pause and write stuff down. That's the great thing about YouTube videos, is you can pause and write. So we need to do the 11 pi over 6 critical number. So we're doing f of 11 pi over 6 equals 2 times the sine of 11 pi over 6. And this is going to be -1/2 minus cosine of 2 times 11 pi over 6. 11 pi over 6 equals 2 times -1/2 is -1 minus cosine of, and what we want is the angle that's coterminal with it. So we'll need to do the same thing that we did just a moment ago with 7 pi over 3. So we want to recognize that the 2 is going to go into the 6 3 times. We're going to get 11 pi over 3 sitting there. So 11 pi over 3, and I wrote 6, 11 pi over 3. So I want to recognize that the 11 can be broken up into a 6 plus 5, and this is times pi all over 3. And when we do this, 3 is going to go into the 6 twice, so you really get 2 pi plus 5 pi over 3. So the angle 11 pi over 3 is coterminal with 5 pi over 3, because when you rotate 2 pi radians around, you get back to the same spot that you were before. So this right here is going to be the same as -1 minus the cosine of, -1 minus the cosine of 11 pi over 3 is coterminal with 5 pi over 3. And then we just need to figure out where on the unit circle we are at 5 pi over 3. And 6 pi over 3 is going to be, 6 pi over 3 would be 2 pi, which would have us 1 full revolution. So 5 pi over 3 is just pi over 3 short of being back to the x-axis again. So the ordered pair at 5 pi over 3 is still going to be 1/2, but the output's going to be negative root 3 over 2. So the x-coordinate's still a half there. So we get minus 1/2 equals negative 3/2. So f of 11 pi over 3 is also negative 3/2. And then we need to, now we've done step 2. So step 1 was find the critical numbers. We did that. Step 2, evaluate the function at each of the critical numbers. We did that. Step 3, evaluate the function at the closed interval endpoints. So that part needs to be done next. I'm going to erase this to give myself some more space to work with. How exciting is that? So now we need to evaluate f of 0, which is going to equal 2 times the sine of 0 minus the cosine of 2 times 0. So the sine of 0 is 0, so we get 0 minus the cosine of 2 times 0 is the cosine of 0, and the cosine of 0 is 1. So we get negative 1. We get that f of 0 is equal to negative 1. And now we need to evaluate f of 2 pi. So f of 2 pi equals, so f of 2 pi equals 2 times the sine of 2 pi. But the sine of 2 pi is going to be 0, and we get the cosine of 2 times 2 pi. So this is going to be 2 times the sine of 2 pi. 2 pi is coterminal with 0, so we really have coterminal angles here. So we should get exactly the same result as we did when we plugged in 0, because we're plugging in coterminal angles. We're still going to get the negative 1 that we got when we plugged in 0. 0 and 2 pi are coterminal, so they generate the same outputs. So there's step 3, evaluate the function at the interval endpoints. And then step 4 is draw a conclusion based on the work that you've done. So I need to evaluate the function outputs and identify which is the smallest. That will be my global minimum over the closed interval. And I need to identify the largest output, which will be my global maximum over the closed interval. So right away, I want to see that 3 is the largest output I got. So I'm going to say the global maximum was 3 at, it happened at pi over 2, 3. So when the input was pi over 2, the output was 3. And the global minimum is going to be negative 3/2. And notice it occurs twice. And it's okay for the smallest output to occur more than once over a closed interval. So I'm going to report 2 different locations. So the global max was 3 at this, or I could say when x was, or when theta is equal to pi over 2. So I could say the global max was 3 when theta was equal to pi over 2 would be another way to say that. And the global min, or minimum, was, or is, probably is a better verb to use there, is negative 3/2 at, it happens in 2 places, at 7 pi over 6 and negative 3/2. And it happens again at 11 pi over 6 as the input. I put a 3 there, that's 6. Those should both be over 6. It reduced in the cosine function to a 3, so I know why I made that typo. So it's at 11 pi over 6. We also got an output of negative 3/2. So there are your global extrema for the trigonometric function over the closed interval from 0 to 2 pi.